In the last episode, we followed the story all the way to its resolution, the discovery of the cosmic microwave background, and the moment the Big Bang became settled science. But that understanding did not exist when these discoveries were first made. To understand why they mattered and why they were so difficult to accept, we need to step back in time to an era when the universe was still very much an open question. As we saw in the last episode, Edwin Hubble discovered that the universe was far larger than anyone had imagined. By using Cepheid variable stars as standard candles, he showed that the Andromeda Nebula lay well beyond the Milky Way, and that our galaxy was only one among many. But Cepheid variables came with a hard limit. They could only be used where individual stars could still be resolved, and beyond a certain distance, they simply faded into the background. As we saw in episode 1, certain stars change their brightness in a steady, repeating rhythm. These stars are called Cepheid variables. What makes them special is not just that they pulse, but that they pulse with precise regularity. The time it takes a Cepheid to brighten and dim tells us how luminous the star truly is. Measure that period, and the star's intrinsic brightness is known. Compare that to how bright the star appears from Earth, and its distance can be calculated. This relationship turns Cepheids into reliable cosmic yardsticks. For the first time, astronomers could measure distances far beyond our local neighborhood of stars. Cepheids transformed the universe from something we inferred into something we could measure. When Edwin Hubble applied this method, the results were unmistakable. Objects once thought to be part of the Milky Way turned out to be far beyond it. The Andromeda Galaxy was not a cloud inside our own galaxy. It was an entirely separate system of stars. Our Milky Way was no longer the whole universe. It was one galaxy among many. With that realization, the scale of the universe expanded dramatically. Space was no longer just large. It was populated. These conclusions weren't speculation. They came from careful observation using the most powerful telescope of its time. At Mount Wilson Observatory, Edwin Hubble used the 100-inch Hooker telescope to resolve individual Cepheid stars in distant galaxies. That capability changed astronomy permanently. It allowed distance to be measured beyond the Milky Way and transformed galaxies from theory into data. Once distance could be measured, the next question became unavoidable. How are these galaxies moving? But before we can answer that, we need to understand how motion affects the light we observe. In this graphic, the source of the wave is moving from right to left. Watch what happens to the spacing between the wave peaks. In front of the moving source, in the direction of motion, the peaks are pushed closer together. The wavelength becomes shorter. Behind the source, the opposite happens. The peaks are spread farther apart. The wavelength becomes longer. The wave itself hasn't changed at the source. What changes is how that wave is stretched or compressed by motion. This change in spacing is what we mean by a frequency shift. When this happens with light, shorter wavelengths shift toward the blue, and longer wavelengths shift toward the red. Motion leaves a measurable signature in light. In astronomy, this shift is not inferred by eye, it is measured in spectra. Every element absorbs light at specific, well-known wavelengths. Those absorption lines form a precise fingerprint. When a galaxy is moving away, that entire fingerprint is shifted toward longer wavelengths, toward the red. Using the Hooker telescope, Edwin Hubble measured both distance and redshift for nearby galaxies. The result was unexpected. The farther away a galaxy was, the faster it appeared to be receding. This relationship was clear in the data. but its meaning was deeply troubling. Hubble did not believe the universe itself was expanding. He suspected some unknown effect in the light, or in space itself, was producing the redshift. The measurements were solid. The interpretation was not. Hubble had uncovered a pattern he could not reconcile with the physics of his time. Resolving that tension would require measuring the universe on a far larger scale. Cepheid variables gave us our first reliable ruler, but they could only take us so far. To measure the universe itself, astronomers needed something brighter, much brighter. Stars about the size of our sun do not die in a single violent collapse. They expand into red giants, shedding their outer layers, and leave behind dense stellar cores called white dwarfs. In some cases, that white dwarf is part of a binary system orbiting with a companion star. Over time, it can pull material from its partner, slowly gaining mass. There is a hard limit to how massive a white dwarf can become. At about 1.4 times the mass of our Sun, gravity overwhelms the pressure supporting the star. When that limit is reached, the collapse triggers a runaway nuclear explosion. The result is a Type 1a supernova. Because this explosion always occurs at nearly the same mass, it releases nearly the same amount of energy every time. That makes Type 1a supernovae extraordinarily reliable standard candles, bright enough to be seen across billions of light years. For the first time, distance and brightness were locked together by fundamental physics. We finally had a yardstick that reached to the edge of the observable universe. And when those distances were compared to redshift, something unexpected appeared. The universe was not behaving the way anyone had predicted. Things got really weird. We'll talk about that in the next episode, so come walk with me.